All right, guys, today we're going to continue with Algebra Nation. This is still section 1. We are going to do topics 4 and 5 together. Topic 4 is about rational exponents, and topic 5 is about adding and subtracting radical expressions. Okay, so I've put it all into this one video, I've put it all into one note sheet, and I've put it all into one assignment. Okay, so I want you to think about your warm-up real fast. If the fourth root of 6 to the exponent of 33 equals 6 raised to the exponent of 33 divided by 4, how do you think we can rewrite the cube root of 7 raised to the power of 4? I want you to actually sit and think about it. Okay, well, I notice that my exponent of 33 is still an exponent. My root now is also in my exponent, but it's as a denominator. So I can rewrite this as 7 to just a single exponent with 4 as my power and as 3 as my denominator. So I moved my root to the bottom. I kept my power 4 up. All right, my next one. If 4 raised to the exponent of 3 over 5 equals the fifth root of 4 to the power of 3, what do you think 6 raised to the power of 2 over 3 equals? Again, I'm going to wait and let you think about it. All right, well, I see this fraction as an exponent. I still have my 3 and my 5. Looks like my 3 stayed as my power and my 5 became my root. So I can rewrite 6 to the 2/3, keeping 2 as my power and making 3 my root, and my base of 6 is what's under the radical. Okay, so let's rewrite following that pattern that we were just working with. Okay, so if I have 9 to the power of 1/2, okay, well, I see a 2 in the denominator and 1 as a power. So I'm going to rewrite it with 2 as a root, radical 9, raised to the power. So 2, the radical of 9, raised to the power of 1. Well, I know that. What is the square root of 9? Right? Because that's the same thing as just saying square root of 9, which is 3. All right, my next one. 8 to the power of 1/3. All right, well, I can rewrite this. Keep my 8 in here. This 3 becomes a root or an index. This 1 becomes a power. That's the same thing as saying the cube root of 8, which I know is the number 2. So if I'm able to rewrite it as a radical, I am also able to simplify it further if I can. Okay, so do we notice a pattern? I notice a pattern. I notice that my numerator becomes the exponent and the denominator becomes the root or the index. So my base and my radicand are the same. My denominator and my index, or the root that we're taking, is the same. And my numerator and my exponent remain the same. So I can rewrite this right here is called your rational exponent. And then this is called your radical. So we can rewrite them back and forth. Okay? I have a little trick for you. I like to think of a tree. Okay? So here's a tree. Here's the base of my tree, right? Looks like I have roots underneath my tree, and the sun is what is giving the tree all of its power to grow. Okay? So if I put it that way, if I rewrite it, I can also say, see how my power is in the sky and my root is in the ground? So that's going to help me remember that my power is always up and my root is always down. So if my root is my denominator, that means our root is always outside the radical, and our power will always stay in the top. Okay. I can also write it as whatever root we have, x, and then all of that can be raised to a power. The parentheses don't matter. It can be one or the other. So I like to think of a tree. Your power is in the sky. Your root is in the ground. That helps me keep in order in my rational exponent what belongs in the numerator and what belongs in our denominator. Okay? So let's rewrite some of these. So if I have 2 to the power of 2/3, I'm going to rewrite it. Okay? Well, I know there's going to be a 2 inside of my radicand because that's my base. All right, my root comes from our denominator, our root on the bottom. So I have the 3rd root, and the power of the whole expression, my power is up in the sky, is going to be a square. Over here, I have a radical with a radicand of 5. The root this time, remember root is in the ground on the bottom. My root here is 2, and our exponent this time is 3. Okay, so now let's use that same strategy with these. All right, I have this square root of x plus 2. So what I'm going to do, well, I need to know, sorry guys, I need to know what's happening. Okay, I need to know what my root is and what my power is in order to rewrite this. So since it's not written, this is a square root, right? So we know that my root here is 2. The power for the entire problem, even though it's not written, technically, it has an exponent of 1. We don't always write the square for the square root, and we usually don't write at the exponent of 1 when it's there. So if any of those pieces are missing, you know what to fill it with. All right, now I can rewrite it. So I know in my fractional exponent, I'm going to have the power, which is up in the sky. I'm going to have a power of 1 and a root of 2. But my base, I cannot just put x plus 2. Because if I do that, it looks like only the 2 has the exponent. So we got to make sure we put it in parentheses because all of this was underneath the radical. So make sure you put it in parentheses when you bring it out. Okay. Our next one, we have a root of 3, but my exponent, it's not written, so what do I know it is? I know it's a 1. Okay. All of x minus 5 was inside of my radical, so I need to keep that together with parentheses. The rational exponent's going to have a power of 1 and a root of 3. And then this plus 2 on the end, it doesn't do anything. It's just going to be there. So we just say plus 2. It wasn't part of my radical, so it's not going to get the rational exponent. Okay. 9 to the power of 1/2. All right, well, it gave me my power and my root. Remember, power's in the sky, root's in the ground. So my root is 2. So a square root of 9 to the power of 1. I could do more with this. Isn't that just the same thing as saying the square root of 9? Which I know is 3. Over here, 16 to the power of 1/2. Okay, so 2 is my root again. 1 is my power again. Okay, so that's just the same thing as saying the square root of 16, which is 4. So whenever you have the rational exponent of 1/2, it's always representing the square root of something. All right, next. All right, let's try some of these. All right, so a 1 over 3 is going to have so we have 8 in here. We have a power of 1. It's in the sky. Our power's always up. 3 is my root. Okay. Okay, so it looks like the power of 1/3 is just the same thing as saying the cube root of something. So in this case, the cube root of 8, which is actually equal to 2. All right, over here we have 125 with a rational exponent of 2/3. So I know 125 is inside my radical. The power of this is what's up top. So my power is 2 and my root is 3. All right, you're going to have to be able to recognize cube roots when you see one because 125 is a perfect cube. It's actually 5 times itself 3 times. So I could also rewrite this as being 5 squared because the cube root of 125 is 5. And now I can square that and get 25. So this simplifies to just 25. All right. Over here, 8 to the power of 2/3. So it's almost like the one above it, except this time my power is 2. So my root is still 3, but my power this time is a 2. Okay, well, we just, right above it, we found out the cube root of 8 is equal to 2, right? So the cube root of 8 squared is the same thing as saying 2 squared, which is 4. All right, our last one on this page, 16 raised to the power of 3 over 4. So this time, let's see, we have 16 inside. My power up top is 3. My root this time is 4. There is a fourth root of 16. That means there is a number multiplied to itself 4 times that equals 16, and that number is 2. And then 2 to the power of 3 is 8. Okay, so this page wanted you to rewrite it and simplify it. So it had a couple things you needed to do. All right, next. I want you to pause the video, and I would like you to try these, and then you're going to push play and check and see if you did them correctly. So go ahead and push pause. All right, check your work with mine. The first one, we have a sum happening inside of my radical. So we had to make sure when y plus 6 came out that it stayed together. So it's still in parentheses. Your root is 5. Your power, even though it's not written, we know the exponent is 1. So my power is 1, base is 5 to give me a rational exponent of 1/5, and then subtract 3 off the end of it. All right, 49 to the power of 1/2. We saw the pattern from before that means the square root of something. So the square root of 49 is equal to 7. Then we had 27 raised to the power of 1/3 that we learned from before. That's the same thing as asking for the cube root of a value. So the cube root of 27 is 3. 3 times itself 3 times gives me 27, right? 3 times 3 is 9, times 3 is 27. The last one is 64 raised to the power of 2/3. So to rewrite that, 2 is my power, 3 is my root. So the cube root of 64 squared, well, the cube root of 64 is 4, and then I'm going to square that and get 16. All right, so I hope you did well. Let's keep going. Okay, we're going to explore now. We're going to start doing section 1.5. So everything we just did is going to help you with the front page of your assignment, which was all of 1.4. Okay, so the front page of your assignment, I think it's 1 through 4, is from section 1-4. This page, this slide is the start of section 1.5. Okay, so this will help you with now the back of your worksheet. All right, we need to remember how to simplify radicals. We did it before. It was part of our review the first week of school. So hopefully we remember. We're going to do a little refresher here with these 5 problems. We want to try to break all of these down. So square root of 40, square root of 8, square root of 54, square root of 27, and square root of 72. So they're all square roots. So I'm going to try to pick pairs that multiply together that involve a perfect square. So it's just going to help me make my problem work quicker. Okay. So the square root of 40, I can break that apart to be 4 and 10. Okay. The square root of 4 breaks apart again to be square root of 2 and square root of 2. The square root of 10 breaks apart to be 5 and 2. Remember we used Mama's rule? So since these are all square roots, Mama's rule is it has to have a pair of numbers or a partner to leave the house. So see right here, a 2 gets to leave a house, but your 10 has to stay, right? So if you could have recognized that the square root of 4 is 2, then you know how that simplifies. Square root of 8, I'm going to break that apart to be 4 and 2, okay? So we're square rooting each piece. Well, the square root of 4 is 2, and the square root of 2 cannot be simplified anymore. So it's 2 square root 2. All right, 54. There's lots of ways to do it, but I'm going to choose the numbers 6 and 9. All right, square root of 6, square root of 9. 6 can only be broken apart into 3 and 2, and there's no pattern there. I'll write it down though, just in case. 9, well, we know the square root of 9 is 3, right? So we know that just equals 3. So 3 is going to come out of the house, but my square root of 6 is going to stay because none of them had a partner to leave the house with. 27, I'm going to use the values 3 and 9. Square root of 3, square root of 9. I know the square root of 9 is 3, so that simplifies to 3 square root 3. 72, you have lots of options. There's 9 and 8. What is it? 12 and something, 12 and 6, I think could work. But what I'm going to use is I'm going to use 36 and 2. Because 36 is a perfect square. The square root of 36 is 6. So I get 6 square root 2. Okay. If you used 9 and 8, okay, so the square root of 9, that is 3. Okay, but the square root of 8 breaks apart to be 4 and 2. There's another perfect square, right? So square root of 4 becomes 2. Multiplies on the outside, so you still get the same thing. Just finding your biggest perfect square as a factor just helps you move through the problem a little bit quicker, but it's not necessary. All right, so why are we doing this? Well, because they're going to help me with adding and subtracting radicals. Okay, we're going to add and subtract them together. So adding and subtracting radicals, let's remember adding and subtracting variables. If I had 4x plus 8x, that gives me 12x. 19RT minus 1RT gives me 18RT. All right, 3x plus 7y, I can't do it, right? It stays that way. So what was I doing? I was combining like terms. So because 4 and 8 both had an x attached to it, they had a common variable, they are like terms. Okay, 3x and 7y, well, 3 has the x attached to it, 7 has the y attached to it. Their variables don't match, so I can't combine them together. Okay, so you can only add and subtract the coefficients in front of the variables if the variables are the same. Okay, so here my variables were RT, here they were both x, here they were different from each other, so we couldn't do it. All right, we're going to apply that with radicals. It's the exact same thing. Okay, but instead of variables, they have to have the same index and radicand. Okay, so that's the same root and the same number inside of the root. Like square root 2 and square root 2, right? I could not do square root 2 and square root 3 because my radicands didn't match. I also could not do square root 2 and then cube root 2. It's not the same thing. It has to be the exact same thing. Okay? So right here, if I have 3 square root 5 minus 2 square root 5, well, they both have square root 5. So I can do 3 minus 2 and get 1 square root 5. And you can write it either way. You can write the 1 or you don't have to write the 1. All right, here, 6 times the square root of 7 plus 4 times the square root of 5. Well, they both had the square root, but one's a 7, one's a 5. I can't do it. They have to be the exact same. So my radicands were different. Okay, so my roots match, they were both square root, but my radicands were different, so we can't do it. Okay, I would like you to try these. Go ahead and pause the video and see if you got them. All right, so check with me. Our top one, they both had a cube root of 7. It was the exact same, so I got to do 12 minus 8 to get 4. Our bottom one, they both have a 5 inside, but my problem here, they have different roots. There's a cube root 5 and a square root 5. Not the same thing, so I cannot simplify. It is done. All right, sometimes it looks like you can't do it, but you actually can. So we also have to always make sure we simplify first. So going back here, I couldn't simplify the square root of 5 or the cube root of 7. I couldn't break it down anymore. So that's why I went straight to trying to add or subtract. Here, I can do some more work before I try to add and subtract, instead of just saying, oh, I can't do it. Okay? So here, square root of 12 plus the square root of 3. Well, it looks like I can't do it, but they both have a square root, so maybe something can happen. I can break apart 12, right, to be square root of 4 times the square root of 3 plus the square root of 3, right? And I know square root of 4 is 2. So now I have 2 square root 3 plus the square root of 3. Okay, I can do something now. Remember, technically there's a 1 right here. They both have a square root of 3, so I can add them together. When I do, I get 3 square root 3 for that problem. All right, so don't say you can't do it until after you have simplified and see what you're working with. All right, now I have the square root of 32 plus the cube root of 16. So guess what? I already know that I can't add them together, but I'm still going to simplify my pieces, okay? Because it is not simplified as low as it can go. I might get to do something along the way. Because we don't know unless we try. So 32 is square root, so I'm going to break that apart. I am going to use the square root of 16 and the square root of 2. The square root of 16 is 4. So that simplifies to 4 times the square root of 2. My other side, we're doing cube roots. So I got to try to think of my cubes. So if you don't know your cubes, you might want to write it on an index card somewhere. Oh, I can't talk and write at the same time. Here we go. Like 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on. So when we're doing cube roots, you want to try to use one of these to break them down. Well, I can use 16 to break apart. I can use 8 to break apart 16. So I'm going to break this to be the cube root of 8 and the cube root of 2. Notice my little 3's on the outside are small, okay? If you write cube root of 8 looking like this, I think that's 3 times the square root of 8, okay? So be very cautious of how you write them. Your roots have to be tiny so I know what they are, okay? Let's simplify. I used 8 on purpose because the cube root of 8 is 2, and now I have the cube root of 2 left over. Oh man, almost. Square root 2, cube root 2, it's both 2, but they're different roots. So technically, that's as simplified as I can get. I can't simplify it anymore. Okay. All right, let's do another one. All right, the square root of 6 plus 3 times the square root of 6. Well, they both have square root 6, right? Technically, there's a 1 right here. So 1 plus 3 gives me 4 square root 6. That was nice. Our next one, square root of 50 plus the square root of 18 minus the square root of 10. All right, so what's nice is they're all square roots, so maybe I can combine something along the way. I also know that they are not simplified. So we're looking for squares, and again, if you're not sure what your squares are, I would write down these somewhere to kind of have handy. I would memorize them probably through like 14, 15. I just don't have enough space. I'm just gonna show you the first 5, but I would try to make sure you understand square root of 1 all the way to the square root of 15. It's a good set of squares to have known. All right, I'm gonna break apart square root of 50. Hopefully trying to use some of this. 25 can go into 50, so I can break that apart to be 25 and 2, because the square root of 25 is 5, so that becomes 5 square root 2. 18, try to use a perfect square. I could use 6 and 3, right? For 50, I could have used 5 and 10, but it's not going to help me as much as it would be if I could put a perfect square in there right away. So 18, I'm actually going to use 9 and 2 to do this one, because the square root of 9 is 3. That becomes 3 square root 2. 10 breaks apart. Only way to break that apart is 5 and 2. Neither of those are perfect squares, and I can't break them down anymore. So square root of 10 is actually just going to stay square root of 10. All right. So look at the first 2 right here. I notice these both have a square root of 2. So I'm going to combine those first 2 pieces. 5 plus 3 is 8. So this becomes 8 square root 2. Still have minus square root 10. Okay, it doesn't disappear. It's still part of the problem. We just didn't get to combine it with anything else. All right. Couple more. This one is the cube root of 2 plus the cube root of 8 plus the cube root of 16. Okay, lots of cube roots. Again, we're going to try to find some cube roots along the way, and hopefully we can match and we can combine. So cube root of 2, I can only separate that to be cube root of 2. There is no breaking it down. That's just going to stay cube root of 2. Cube root of 8, well, that's nice. I know that. Isn't that just 2? Okay. Cube root of 16. Okay, well, that's not a perfect cube. I can break it down, though. Again, try to use our cubes. So like 1, 8, 27. Okay, so I'm going to use the cube root of 8 and the cube root of 2 to break apart 16. And I know the cube root of 8 is 2. And we're going to keep this cube root 2. Okay, so I have 1 in front of here. I specify that because I see this cube root 2 and I see this piece with the cube root 2. So I get to put those together. 1 plus 2, that gives me 3 times the cube root of 2. See why it's important to have a little 3 and a big 3? And then we still have the plus 2 on the end. It doesn't mess anything up. It is still part of our problem. We just don't get to combine it with anything else. So it's still there. All right, I believe this is our last one. Square root of 200 minus square root of 72. All right, square roots. Let's think of those. We have 4, we have 9, we have 16, we have 25. We're going to try to think of those. 36, 49, 64, 81, 100. Can go all the way up. 121, 144. Okay, so looking at the square root of 200, I can break that apart using a perfect square of 100. 100 times 2 is 200, right? Because the square root of 100 is 10. So that becomes 10 square root 2. Now, if I didn't know my squares, I might have tried like 50 and 4 or 25 and 8, right? Which again, I wouldn't be wrong, but it's not the highest, and there would be more work for me to do. So trying to find your highest perfect square is going to help you do the problem quicker. All right, 72, again, your brain might go to 9 and 8, but watch out. We did this one earlier, I think. This can actually break apart to be 36 and 2. The square root of 36 is 6, so it becomes 10 square root 2 minus 6 square root 2, they have the same root, they have the same number inside of the root. I get to actually subtract 10 minus 6, and we're going to get 4 times the square root of 2. Okay? So that's the end of our notes. You can stop the video here if you want to, but my next slide is actually a problem from your homework that I'm going to work through. So I advise you to stay. Or if you want to try this problem on your homework first and then come back and check, you can do that too. Okay, so the notes are done. This next slide is part of your homework. Okay, I believe this is number 3 on your homework. So it wants you to check all of the expressions that are going to simplify to be x over 7 over 4. So this is what we're trying to get each time. If they simplify to that, then I'm going to check yes. And if they don't, we're going to check no. All right, the first 3 looks like I'm just rewriting from radical form to rational exponent form. So this one right here, I have an x. My power is 4, so it's up in the sky. My root outside is 7. That is not the same thing. That's a no. All right, let's try this one. Let's see if switching them helps. X is my base. Now my power is a 7, and my root is a 4. Hey, that matches. That's what I want. That is equal to the same thing. The third one looks just like the second one, but there's parentheses and a power on the outside. We talked about how that doesn't change anything. 7 is still my power, 4 is still my root, so that is still what I want. All right, the fourth one is trying to trick you, okay? There is a square root going on here, and all of this is also being raised to an exponent of 1. So if we see a radical symbol, there should be a root and an exponent attached to it, all right? So technically, I have... I'm going to show my work over here. You should show your work also. I have x to the power of 7 over 4 inside of my radical, which has a power of 1 and a root of 2, like that. Oh man, here comes our power, our property of exponents coming back to us. So I got to remember, power to a power, right? No, go back. Power to a power, I get to multiply those together. When we multiply fractions, we can just go straight across the top, straight across the bottom. So this gives me 7 times 1 is 7. 4 times 2 is 8. That is not what I want. That is not equal. All right, I have work to show again on the next one. I'm going to convert both of these to exponents first. Okay. So I have, because right now I can't do anything with them. So let's put them, let's rewrite them. 4th root of x to the 5th power. I'm going to rewrite that to be x. It had a power of 5 and a root of 4. Okay. And we're going to multiply that. This is x. This one has a power of 2 and a root of 4. Okay. So another property of exponents. Because my bases are the same, I get to add my exponents. All right, my exponents are fractions, so I have to make sure my denominators are the same. They are, they're both 4. So I can just add across the top. So this simplifies to 7 over 4, which is what I want. So that one is a yes. All right. I'm going to set up the next one just using the same strategy. So here I have x. Oh, you can't really see that, can you? Let's change. Let's do purple. Okay, so here we have x. It has a power of 4 and a root of 5 times another x with the power of 4 and a root of, looks like a 2. All right, so again, I'm going to get to add my exponents, but my denominators are not the same. Let's make them the same. Let's make them both have a denominator of 10. So to do that, I'll multiply my first exponent by 2. So it becomes 8 over 10. And then my next one, let's multiply that fraction by 5 to give me 20 over 10. Now I can add them together. That gives me x raised to the power of 28 over 10, which simplifies to, what is that going to be, 14 over 5? That is definitely not what I want. So that's no. All right, last one. All right, so I have a fraction this time, a quotient, but look at my denominator. It's being raised to the 0 power. What does that tell you? It equals 1. Anything to the 0 power is equal to 1. So that's just the same thing. If it's divided by 1, I just have the 4th root of x to the power of 7, which I can rewrite as x power of 7 root of 4, and that is what I want. So that one works out to be what I want. All right. This was number 3 on your homework. Okay, you have a problem, another one like it, number 4. I think what you're trying to match it with is a radical, but same process. Make sure you show your work. As you can see, there's plenty of work to show, especially those bottom 4 problems. Okay, I have to show work here. Those first 3 were kind of, I guess I could have done it in my head, but I like to write it down and show myself because I might assume wrong. Okay, so that's the end of the video. Get going on your homework, and I think I'm going to hold a Zoom to answer any questions that you might have. All right, bye.